Welcome to Step 5 of the TTP-Based hunting methodology training. In this step, we will discuss identification and mitigation of data collection gaps. We will begin this module with a general overview of the hunt methodology training. We will then move into the module proper by discussing identification of data gaps. This will include identification of current data sources as well as how to use threat emulation tools to identify where gaps may exist. Once the gaps have been identified, we move on to addressing those gaps. We can either close them, adjust analytics to compensate for any known gaps, or, in the event that we cannot find a resolution, communicate the impacts of any remaining gaps to the network owners. We must validate the configuration of our data sources by ensuring end-to-end data flows and that all data is generated, collected, parsed, and indexed correctly. We will conclude the module with a brief summary, followed by an exercise designed to help you practice the techniques discussed. As you can see, here in Step 5, we are slowly starting to rebuild the solution for the problem decomposed on the left-hand side of our hunt methodology V. Before this step, we were in the filtering stage, and in the following step, we will be implementing and testing analytics. As we mentioned in previous modules, although this model appears linear, it is expected that you may need to cycle back to previous steps as new discoveries or issues arise. This iteration is beneficial, and the model supports this by providing a framework upon which you can build and iterate as you implement. At the end of this course, you should have the knowledge you need to complete this process on your own. In addition to leveraging the work of the broader community, you'll be able to develop your own analytics and craft what you get from outside sources. So what are we trying to accomplish in this step? At the conclusion of this training, you should be able to identify any gaps in your data collection within the environment in which you are attempting to find adversaries, be able to develop a data strategy, and provide a plan for addressing any gaps you have identified. To achieve this, you need to know how to identify current data collection configurations, determine data collection gaps between the current configurations and the requirements we defined in Step 3, and create a plan to address those gaps. With a plan in place, we begin to work on closing the gaps using a variety of methods, which can include reconfiguring any existing tools, deploying new sensors, establishing data flows for new data, and possibly using alternative analytic approaches using the data you have available. After that, we will need to validate new data collection configurations, identify any remaining gaps that may exist, and be able to communicate those gaps to the network owner. Just like the previous modules, you should be familiar with Windows, an analytics platform like Splunk or Elk, the fundamentals of networking, and attack before beginning this course. If you want to gain hands-on experience, you should also have an analytic environment in which you can instrument with sensors and an analytics platform to experiment with your own analytics. Let's review what we've covered so far. In Step 1, we learned how to take TTPs from threat intelligence and identify those that we are interested in developing detections for. In Step 2, we took those TTPs and developed hypotheses for how we might detect them. In Step 3, we decomposed those hypotheses into data requirements. And in Step 4, we filtered those requirements based on the environment in which we wanted to develop the detection. In this step, we will deploy the tools and configurations that support the detections themselves. This will include identifying what the current data collection configurations are in the environment and identifying gaps in what is and what we need it to be in order to build the analytics themselves. We will also need to address any gaps that still exist afterwards. The first topic we will cover in this module is how to identify gaps in data sensing. This encompasses ensuring the right kind of data is being generated in the environment, that the data is being sent to the analytics platform, and that the data is available to the analyst. This step can be particularly challenging to perform if coming into an environment you are not intimately familiar with. It can often involve needing to set up meetings with many people from across the organization, as one person doesn't have all the answers. While this may not be the most fun step, it is critical to perform in order to understand the environment you are operating in and to maximize efficiency. There are 5 primary methods we can use to assess gaps in data generation, each one relating to a different aspect. First, and perhaps the most obvious, is to identify what kinds of data are already being generated in the environment, what is generating them, and what are the configurations for those tools. This gives you an as-is picture of the current data sensing available to you. Similarly, we want to collect as much information about the environment itself as we reasonably can. Specifically, we are looking for things like network maps and generic system information for the devices spread throughout the environment. Ideally, the network administrators would have something like a network topology and system inventories readily on hand, but this is often not the case. We don't need the locations of every single device on the network, but we need to know where things like network boundaries are, where firewalls that might interrupt the flow of data are located, and where is data currently being aggregated, if it even is, and are there any processing or storage limitations that we should be aware of. Thirdly, we can look at artifacts from any past coverage assessment that has been done. What exactly coverage means may vary depending on the method used to assess the coverage. Some assessments may look at adversary TTP coverage, which for our purposes would be very useful, as it immediately shows us if the detection we want to implement can be done without changing the environment. Others may look at specific capabilities. For example, whether tools like antivirus or firewalls are deployed and where. The important thing here is to try and leverage existing work wherever possible to make your life easier. If we believe the existing infrastructure has the data generation and flows in place that we need, then we can always try executing the TTP ourselves and looking for the expected event in our analysis platform. This method is better suited for TTPs that are sometimes referred to as living off the land techniques. These are techniques that use pre-existing tools in the environment to perform the activity, thus making it easier to get network administrator permission to execute the TTP. And you should definitely get permission before running suspicious commands and programs, lest you worry any other network defense staff. If you don't, it could damage trust with the network managers, making your life harder. Ultimately, all these methods serve to provide you enough information to identify where data generation for the detection you want to write is lacking. There are lots of options for where gaps can exist, but here are some common examples. There is no tool deployed to generate the required data. Or maybe a tool is deployed but is not configured to send the necessary data yet. Or the data is being generated but not sent anywhere. A firewall is blocking data from reaching the analysis platform, or the tools are deployed inconsistently in the environment. So why are we going through all this effort? Why not just tell network managers, deploy this tool for me? The truth of the matter is that unless you are doing all this in your own lab, there are many moving parts and equities that can come into play. By doing your homework, we can build trust with network owners and managers, and they'll be more likely to cooperate when requests are well informed. The why of needing to identify current data sources and configurations is that we need to be able to compare our data requirements against what the current state of data centers are in the network. This will enable us to identify any gaps that may exist in what we need versus what we want. We do this a variety of ways, a lot of which will involve talking to network managers, network architects, and system owners. Depending on the details of the network, some things to look into are the seam, any available configuration files for existing tools, and group policy settings. Some of the things that we are looking for in those sources of data are what kinds of data are those data sources making available? Where are those tools deployed? And how often and how is that data being collected, if at all? How are those tools currently configured? And for what kind of activity should data be generated? It is important to ask these questions, as we cannot assume that the environment is censored consistently across its entirety. When having these discussions, it can be helpful to keep the time-terrain behavior paradigm in mind to help inform what questions to ask. While you might expect the terrain aspect of our time-terrain behavior paradigm to be our primary consideration in this step, time also plays a significant role. I've often seen this component being overlooked, at least initially, and it is only reviewed later on when problems start to arise. This can have a significant impact if it is not considered early on. For example, if you are in the middle of an incident, but your data is taking 24 hours to get sent to the SIEM and available for analysts to use, you will always be at least 24 hours behind your adversary, making timely responses virtually impossible. It may also impact the functionality of certain detections if they are designed with a certain time frame in mind for collection. So, one of the first questions we want to ask ourselves when thinking about time is, what is the time interval over which existing data is collected, aggregated, and sent on to the SIEM? Is data sent continuously from endpoints and sensors to the SIEM? If so, is it generated and sent in real time, or is it perhaps collected in real time but sent up periodically? Many tools work by taking snapshots of information and uploading that to the analysis platform. This has the advantage of reducing data volume, but may open up the possibility of missing critical information if it happens between snapshots. A third option is data collection on demand. That is to say, it is only collected when an administrator instructs the tool to collect the information. Often this is best used when collecting very high volume data that is impractical to collect regularly or data that is not needed most of the time. A good example of this kind of data is memory images for use in forensics. Assuming data is currently being collected, another important consideration is identifying the retention policies of the different kinds of data. By retention, we mean how long is data saved before being deleted. There is always a trade-off being made here between wanting to hold onto data for use in searching and the realities of not being able to save all data forever. It is important to know how long data will be stored, and once it is removed, it cannot be searched, which may hamper investigation efforts. Sometimes the data retention policy is based on data volume rather than time, or a combination of the two, which can make figuring out how long data is stored trickier. But often you can get an idea just by looking at what the oldest event is or calculating based on the average amount of data generated per day. It is also important to note how long data is retained at the various steps that data transits before it reaches the SIEM. For example, you can have data being collected continuously on endpoints, and the data is sent to the log aggregator in near real time. However, the aggregator itself only sends the data to the SIEM every 24 hours. So, from a data generation perspective, the data collection is continuous, maximizing our likelihood of capturing necessary data. But from an analysis perspective, the data is only available basically the next day. If our detection that uses that data is also run on a schedule, for example at night, then there could be up to 48 hours between the time an event happens and when an analyst sees it to begin investigating. You can maybe see how quickly this can add up. Another consideration to keep in mind when looking at data collection is ensuring that timestamps are standardized and synchronized across data sources. In Windows environments, the first step of ensuring this is connecting the endpoints and servers to a network time protocol server, usually referred to as an NTP server. This is usually sufficient in small organizations, but complexity can arise when you start looking at data from other time zones or incorporating data from non-Windows devices. For example, let's say you are working in a SOC on the East Coast of the United States. Data from your region comes in fine, no problem. But when you add data from other time zones, you start running into issues. Is the data from other time zones coming in as UTC or with the time from their time zone? Trying to correlate data between endpoints across multiple time zones in their respective local times can be very difficult. Also, are all the data sources normalizing to UTC or the standard time, or some in local and some in UTC? As an analyst, which version of time do you see? Do you look at events in UTC or in your local time? Not considering this can bog down investigations, break time-sensitive and correlative analytics, and lead to false conclusions. Terrain is perhaps the most obvious thing to consider when assessing data collection. We need to know where sensors are deployed, on what devices, and what kind of coverage does that get us on the network overall. It is important to keep in mind that not all terrain may be obvious when asking this question. For example, are mobile devices part of the terrain that you are taking into account? What about network segments that are segmented off from the primary network, like a DMZ, or protected like a SOC's network might be? You don't necessarily need to instrument everything, but you should at least be aware that they exist and can potentially provide terrain that an adversary can use to infiltrate the network or perform activities in. When planning out a sensor strategy, keep in mind that you may not be able to collect the data you want from everything, whether because of technical or policy reasons. Some systems or subnets may be of particular interest to adversaries and may be worth extra monitoring in case they are compromised. Some of the devices are sometimes classified as crown jewels, or systems who are critical to the functioning of the business or of critical information that can have serious ramifications if they are compromised. Certain devices or locations may also serve as choke points that an adversary is likely to or must travel in order to progress through the network. If we are savvy, we can use this information to our advantage when looking at sensor placement and make sure these locations are instrumented. This often comes up when looking at network sensor deployment, where there are obvious paths through the network. In some instances, just instrumenting the network boundary may be sufficient, as any outside malicious activity would need to transit it. But if we want to capture traffic between subnets, we may need to instrument lower-level routers. Capturing data from these choke points gives us the opportunity to respond to adversary activities most effectively. It is also important to keep in mind the behavioral aspect of the data we are looking to collect. After all, the data is being collected to detect a particular behavior. Ultimately, the data needs to be sufficient to provide insight into the behavior we want to detect, and ideally any behavioral invariants that we have previously identified. In addition, we want the data that we collect to also provide further information that can be used to assist in an investigation. The additional data fields we want to make sure we have depend on the events we are looking at, but a good rule of thumb is to think about what data fields would help you relate it to other events. Some good examples of this are hostnames, IP addresses, parent process IDs, etc. Now, adversaries will also be actively trying to evade our efforts to detect them. We need to take this into account when deciding which data to collect. There are several ways we can do this. one of which is to collect a secondary data source that provides similar information to the primary data source. This needs to be a carefully considered decision, as collecting redundant data will increase the data storage and processing needs. Another option is to collect logs that can indicate when tools have been tampered with. Many sensors will output log files when the state of the sensor is changed, for example, being enabled or disabled, or if a new configuration is saved. This can be much more efficient from a data storage perspective, as these events don't happen nearly as often, typically. On the SIEM side, we want to be prepared to monitor for instances where data feeds go down or systems stop reporting. Some of this will be noticed if we monitor for state change events from data sources, but we can also more simply monitor for data sources or hosts that stop sending events to the SIEM. This can be indicative of malfunctions or malicious tampering, either of which we should be concerned about. The tricky part of monitoring in this way is how does one separate normal gaps in data, like a computer being shut off, versus malicious activity. So far, I haven't found a solution to this problem, but some things to look for are, if all the sensors are down, maybe the whole computer has been shut down. If many computers are not reporting anymore, maybe an aggregator is down. Or if only one sensor is down on a given computer, check for any logs that you have from immediately preceding the gap that may indicate what happened. Process events are often a good source of data in this regard. Here is a simplified notional network that shows some of the questions we want to ask when assessing the state of data collection in the environment. We have a group of endpoints that access the internet through a router with a SIEM separated off into its own subnet. For the endpoints, we need to assess how many hosts are even out there that we need to defend and collect data from. We need to know what their operating systems are in order to get an idea of what TTPs might be relevant. We also need to know how the various subnets are laid out so we can instrument the network effectively if we are collecting network data. The endpoints send their logs up to log aggregators to be forwarded on to the SIEM. Here, we need to know at a minimum how many aggregators there are and where they are located. Additionally, we should consider getting metrics on how much storage those aggregators have and how often data is sent up to the SIEM. We also need to know which data sources are being sent to each aggregator. This knowledge can be critical in troubleshooting data flows when they are not working. In the middle of it all are the routers that direct the network traffic. Here is where a network map can be very handy. In some situations, we may want to get the routing rules as well, but this is primarily useful for troubleshooting or assessing how an adversary could potentially move through the environment. Facing the internet, we have firewalls and possibly network intrusion detection systems that have insight into network traffic going in and out of our environment. We need to know how many devices there are and how many exits to the internet there are. Noting perimeter devices in particular can help us focus our sensing for exfiltration and C2 techniques. We also need to know what rules are in place so we know what communications can possibly transit the perimeter. Data from all these devices will be going to a SIEM located on a separate subnet from the endpoints. The routers need to be configured to allow the data from across the environment to reach the SIEM. SOC analysts have their workstations on the same subnet as the SIEM and try to keep all security relevant machines secure from any compromises that may occur in the network. If a threat assessment of the environment has been previously conducted, it might look something like this. This is a heat map of attack TTPs and the coverage that the current data sensing provides. An assessment in this format immediately answers our question of whether a data source is generating data for our TTP. On this diagram, white TTPs have no data being generated that address the TTP. Yellow means that the TTP is covered to some degree, but not completely. Often this means that certain implementations of the technique are not covered. Green means we are generating data that can detect all implementations of that technique. Since the bar is very high for detecting all possible implementations of a technique, under this metric, most TTPs will fall under no coverage or some coverage. The likelihood of having complete coverage is small. It is important to note, with an assessment like this, that it only informs you what TTP coverage is possible, not what is actually being detected. Some of the things that might not be captured here are how consistently tools are deployed in the environment or consistently configured. This often leads people to believe that they may have certain TTPs covered, but later find out that for whatever reason, they have no visibility of them. Note that this also doesn't give an indication of the false positive rate that you may encounter in any existing detections. This kind of visualization is useful for tracking TTP detections as they are developed. As more detections are developed, better and more granular visualizations can be developed to track the organization's detection capabilities. Once this becomes more fleshed out, it can be very helpful at step 0 when determining which TTPs to start trying to develop detections for, as it can serve as a guide for what is currently possible and where gaps are. The final method we will discuss for identifying gaps is to perform the activity like an adversary would and verify that you can see the resulting events in your data. Some techniques are easily reproducible through commands or actions using tools built into the systems being monitored. Others, however, require using specialized tools that emulate adversary behaviors. There are several tool suites that exist in the commercial world that facilitate this kind of emulation, including MITRE's Caldera, Cobalt Strike, and Metasploit, to name a few. The primary purpose for using these tools is to validate that our sensing deployments and configurations will generate data that we can use to build detections on. In order to effectively do this, we need to have carefully considered what kinds of data we are going to look for back in step 3. If we don't know what kind of data to look for and what that event should look like, we might waste significant amounts of time here looking for an event that doesn't exist. Conversely, we may also identify additional events that are tied to the adversary behavior that we did not initially consider. It is important to note that we are not conducting a vulnerability assessment of the system or network, often referred to as red teaming. The purpose is just to validate that defenders can see the adversary's actions. Therefore, it may be necessary to temporarily disable a security control that may be in place in order to perform the required activity. Now, you might ask, why would we worry about a technique if the system prevents it? And the answer is simple. We can't assume that just because a security control is in place, that an adversary will be unable to perform the activity. They may disable the security control before performing it, or execute it using an unanticipated method. We should always assume that adversaries will find a way to subvert security. Now that we have identified where gaps exist in our sensing, we can begin to remedy or mitigate those gaps. The goal is to bridge as many gaps as we can and plan for any we can't. Where the previous section is very much about planning, this one is a lot more about doing. There are a couple ways we can address gaps. The first of which is to just close the gaps. The best method for closing gaps depends heavily on the gap in question. In the event that we have a sensor deployed that can meet our needs but is currently not configured to collect the correct data, then likely the easiest option is to update the tool's configuration to collect the additional data. If the tool is configured correctly, but not deployed throughout the environment enough to cover our desired terrain, then we can ask that the tool's deployment be extended to other network segments. This can sometimes happen when a tool is being tested or is deployed in a limited fashion for whatever reason. If there is no tool on hand that can provide the data we need, then we need to deploy the sensor that best meets our collection needs. This is often a longer process than adjusting existing tools, since we'll often need to convince the network owners that the additional tool is necessary and won't negatively impact their network, or at least convince them that the impact will be minimal. After that, new processes will need to be put into place to deploy the tool and configure the existing infrastructure to integrate it. If we are not allowed to reconfigure or deploy our tool of choice, we may need to pursue alternative options. This could be a similar tool that, for whatever reason, is suboptimal, but better than nothing. A good example of this might be a tool that provides snapshots of data rather than a tool that monitors continuously. We can also try to mitigate the gap by compensating in the analysis platform. Depending on the data we have available to us, we might be able to infer the data we want. For example, if we want visibility into logins on endpoints, but we are not allowed to collect authentication logs, one alternative is to look at certain process create events that indicate a login, like winlogon.exe. This won't give us the fidelity we desire, but we will at least know around when a user logged into a system. It is important that we capture the limitations of these alternatives and communicate them to the network owner. Doing so may help us persuade them to allow us to deploy or reconfigure the optimal tool option in the future. Similarly, for any gaps that we can't address, we also need to capture the impacts that those may have on our ability to detect adversary activity. When doing this, it is helpful to trace the gaps back to the TTPs associated with them and use those to indicate how these gaps will prevent detecting those TTPs. When we frame visibility gaps from the perspective of TTPs, we can then articulate on how those unseen behaviors can present adversaries opportunities to perform activities unseen that can impact the network. By communicating the potential risks and impacts this may have on the network owner can make informed, risk-based decisions about the defense of their network. One way we can visualize these impacts is using the same attack heat map we discussed a couple slides back. The red, yellow, green notation is easy for non-technical managers to understand, even if some technical details are lost. When deciding whether to deploy a new tool or reconfigure an existing one, we usually prefer to reconfigure an existing one, largely because it doesn't require additional permissions or approvals. Since the tool is already in the environment, we can reasonably assume that there will be few unintended consequences, depending on the nature of the change, of course. One of the major unintended consequences that can occur when deploying a new sensor, especially one on endpoints, is that security tools can often conflict with one another, causing them to malfunction or stop functioning altogether. This particular problem is not always obvious and may not be noticed till an investigation is underway. Tracking which tools are sending data to the analysis platform is one way we can identify this kind of issue. An additional benefit of using existing sensors is that we won't need to architect new data flows or parsers to get the new data to the analysis platform. Some modifications to the existing configurations may need to be made though. Sometimes we just don't have the option to use existing tools. Sometimes because the network owner is unwilling to allow modifications of them, and sometimes because the existing tools just can't meet our needs. This is the primary reason why we would look to deploy a new tool or sensor. Deploying new tools gives us the opportunity to choose a tool or tools that best meet our time, terrain, behavior requirements. The downside, as I previously mentioned, is that there might be unintended consequences, and we'll need to architect the data flows to make sure the data gets to our analysis platform. Let's look at an example of making this kind of decision between modifying an existing tool in this case built-in Windows logging via group policy or GPO, and deploying a new endpoint detect and response tool or EDR. For this example, we need to collect logs for the creation of new processes with command lines, and have concluded that we can use a GPO modification to do this, or an EDR that we have access to but is not currently deployed. To help in making this decision, we've listed the pros and cons of each option. For modifying Windows auditing via GPO, the pros come largely from the environment already being set up to push out changes through GPO and having Windows logs sent to the analysis platform. Since this uses existing tools, we don't need to worry about additional licensing, other than perhaps on the analysis platform for ingesting more logs. Some of the cons with this solution are that we may need to modify several separate tools to enable this data to reach the analysis platform, as a GPO change will only affect the endpoint collection. Windows event collectors may need to be reconfigured as well to ensure the data is forwarded on for analysis. This method also requires that there is local expertise in how to manage GPOs and that those staff have the permissions to do so. In large organizations, this may not be the case, as corporate policies may be managed elsewhere. Since the GPO change will just generate more logs, we will need to spend time writing analytics ourselves to get value out of these events, which may be additionally challenging if we want to build correlations between different kinds of logs. Some of the major advantages that we may get with an EDR is that they usually come as a complete solution, meaning we will have detections built in, saving us time on the analytic development side. Most licensed products also come with some kind of tech support, so we don't need to train and keep complete experts on the team and can request assistance when we encounter issues or need help. EDRs also tend to have intuitive and developed user interfaces, making the analyst's jobs easier, or at least reducing the required expertise to use the tool. A few of the biggest cons to using a new EDR are that it will cost additional money to acquire, and depending on the scale could get quite expensive, and we will need to develop a configuration and deployment process for the environment, each of which can be a large effort on their own. In the previous slides, we saw some of the pros and cons of modifying existing sensors compared with deploying new ones. Regardless of whether we are rolling out new tools or modifying existing ones, we need to have a thought-out plan of how we are going to do that and what the end state will be. We need to make sure that we carefully consider and write down how we plan on configuring, deploying, and managing these tools. It is not enough to just say, "Install this for me." This leaves too many questions open, like install on which or how many hosts? When should it be deployed to minimize user impact or avoid alerting the adversary? Which features of the tool should be enabled, or who is going to be responsible for managing the tool afterwards? There are also tangential but important questions to ask ourselves, like how will the data flow to the analytic platform? And who will set it up and manage it? How? What is the impact on system and network resources that this change will have? And will they be a limiting factor in what we can do? And will this tool even work across the range of platforms and technologies we want to deploy across? Or do we need to accept that some technologies won't work with others? Too often, people do not consider these questions prior to making changes to the environment and assume the answer to them. And if the assumption is that it is someone else's responsibility, that person may not agree. Going in with a well thought out plan may help convince network managers to agree with your plan if it appears well thought out and they can see potential consequences before they happen. You may recall our example network from a couple of slides back. Here we have fleshed it out a bit more with things to consider for different segments and added data flows and an additional sensor. Ultimately, all data is set to flow to the seam, but we have identified that said data will come from several different kinds of devices, each following their own path to the seam and the analyst's screen. We have clarified from the previous map that there is a log aggregator set up for endpoints to forward logs to, as well as define what the firewall is between the internet and the enterprise network. We have also added a network tab on the router in order to collect network traffic. Once the host sensors on the endpoints are deployed, configured, and properly sensing data, that data is sent on to the log aggregator. Here, a log forwarder takes the aggregated logs and forwards them on to the seam through the router, which needs to be configured to allow the data to reach the seam, which is in a protected subnet. The firewall data gets sent directly to the seam via the router, rather than going through an intermediate aggregator, since there is only one such device. The NetFlow sensor, labeled as network tap, copies the packets passing through the router and analyzes them for irregularities. In this instance, the PCAP and NetFlow are forwarded on to the seam for retention and analysis, notably bypassing the router. This device will enable us to capture the data required to find instances of remotely scheduled tasks, per one of our hypotheses defined in Step 2. Since all the data is sent to the seam, the analyst needs access only to one system, the seam itself, in order to search across data from the myriad of data sources flowing into it. This helps reduce the number of credentials an analyst needs to do their job and generally simplifies their processes if they can go to a single system to do their job rather than many. The following two slides are a more in-depth breakdown of the previous diagram with some of the things to think about for each element. This is certainly not meant to be comprehensive, but hopefully will give you some things to think about. Along the top, we have the different objects that are captured in the diagram, and each row is a specific thing about each object that we need to consider. For example, under inputs for firewalls, we need to ask ourselves if we have visibility of all traffic passing between internal and external networks. You may notice that endpoints here have no inputs. For the purposes of keeping this diagram simpler, we have left it blank as there are no data flows going into it, but you could capture users or various peripheral devices as inputs if you wanted to take the diagram to a more detailed level. Each person or group will have their own level of abstraction that fits their needs, but we feel this level fits the general case well. We encourage you to pause the video here and take a moment to read the slides in more detail. As you can see, we also have breakdowns for seam, log aggregators, network taps, and analysts. There are some interesting things to note here. The aspects of seams that we will tend to care the most about are the inputs and configuration. If data is not ingested into the seam correctly, then it will not provide much value to creating and using detections. Similarly, if the seam is not configured correctly, analysts will not find it useful, and it won't matter how much data you are ingesting if it can't be used. As you might imagine, inputs and outputs are perhaps the most important factor for the log aggregator, since its primary role is to take logs in from multiple devices and forward them on or retain them till they are collected. I encourage you to take a moment again and pause this video to read each of the cells and think about what other considerations there might be for each of these devices. Let's look at our scheduled task example. Back in step 3, we identified that we need to collect data that contains principal user and subject user fields. We know that both Windows Event 4698 and 106 are triggered when a scheduled task is created, but only 4698 events contain the fields we need. Thus, we can safely say that 106 events will not meet our data needs. Now that we have decided on collecting 4698 events, we need to figure out how we can collect them. If we were just collecting from a single host, we could open up the local group policy editor, as seen in the screenshot here, and enable collection of successes under Audit Other Object Access Events. Since we want to collect events from across all Windows systems, however, we need to look at updating the group policy domain objects for the whole domain. With those objects pushed out, we should start collecting all such events. It may be helpful to try the group policy change on one or two systems before deploying to the whole environment. While we can expect that there likely won't be any tool conflicts to worry about since it is a built-in Windows utility, we still want to verify that the change works as expected to get an idea of what the log generation rate might be. Sometimes we have to compromise in what data we collect and take a less ideal sensor option due to factors beyond our control. We may be forced to fall back on our secondary or even tertiary option for generating our desired data. This could be due to several factors. Licensing may be prohibitively expensive to deploy throughout the environment, or the process of acquiring such licenses may take too long to complete if there's an immediate need. Alternatively, we might just not be allowed to by the network managers. Even though they may initially refuse our request, if we can convince them of the value of doing what we ask, then we might be able to get our first choice of sensor. It often helps to communicate to the network owners why we want to make the change, what effect we expect it will have on the network, and what are the benefits. If the problem is lack of technical expertise in the tool, then perhaps training can be arranged, or if the local administrators lack the necessary knowledge, then we can work with them to implement the changes. This effort can help build trust between teams when done well. We may also just not have the hardware to support our preferred plan. Maybe our servers are just too old, or they are already maxed out. Purchasing new hardware may be a solution, but like licensing may be difficult to accomplish in the short term. Why do we need to communicate with network owners? Normally, we are trying to do one of two things. Either convince them that they need to act in order to allow us to close gaps we have identified, for example, enabling more auditing through group policy objects, or we want to simply notify them of the limitations of our current sensing capabilities. In other words, we don't expect them to take any action. Sensing and detection gaps present opportunities for adversaries to remain undetected, which if left alone will likely eventually cause negative impact for the network owner. For example, exfiltrating business intellectual property or wiping databases. We need to be able to communicate how the gaps in sensing that we find translate to these impacts so they can be more easily understood by the network owner. When we do speak to network owners, we want to make sure that it is more of a discussion, rather than making demands or just throwing a report down on their proverbial desk. But what are some ways we can do this? The issue we often face is that simply telling them a gap exists and what it is isn't enough information for them to make a decision. Many network and business owners have little to no idea about cybersecurity or adversary TTPs. Thus, we need to frame the conversation in terms that they can understand. Business and network owners will most easily understand the necessity of addressing gaps if they can understand how the TTP gaps translate to potential impacts on their operations. For business owners, it might be framed in loss of intellectual property or amount of time the business will be unable to operate, thus costing money. For network managers, the impacts can often be framed in a more technical way, but not necessarily at the level of individual TTPs. Potential damage to equipment or increased system downtime due to ongoing investigations are two possible impacts that are important to any network manager. In order to do this, we need to retrace the data gaps back to the related hypotheses and TTPs. In other words, we need to draw a connection from the data we want to collect to the TTP we are trying to detect, and why that TTP is important for us to detect from the network owner's perspective. For example, Let's start by explaining that the data we are looking for supports the detection of a certain TTP. This TTP is used by adversaries to perform a certain tactic, which can have a negative impact on their operations, and then explain what the impact of that would be. These kinds of discussions will often be held to discuss multiple gaps and TTPs that need addressing. We should think about what our priorities are in terms of which TTPs we need to have covered versus which would be nice to have. We and the network owners will probably be resource constrained, so we need to provide some way to establish which TTPs we want to focus on. Some things we can use are how relevant that TTP is currently. For example, are threat actors currently using the TTP? And are these threat actors of interest to us in this instance? If the TTP in question is not actively in use or relevant in the environment, we may want to prioritize closing the gaps that address more relevant TTPs. We may have a limited window of time to present our case, so we need to carefully consider how we want to present our case. We want to clearly present what actions we are expecting them to take or what approvals we are seeking, and how our ability to conduct the hunt is negatively impacted by the data gaps we have identified. For each option, we should try to present a cost and benefit analysis for each, so that the network owner can make an informed decision on which course they want to follow. The options and the cost-benefit analysis of those options provide the foundation for our discussions with the network owner and to help frame it, as well as making it easier to arrive at decisions. We need to make sure the costs and benefits are framed in a way that the network owner understands and is relevant to their role. When having this discussion, consider bringing supporting documents and visualizations that might help make your case. Attack heat map visualizations, for example, provide an easily understandable visualization that can be used to show overall coverage of TTPs. These visualizations can then be overlaid with mappings of which TTPs a given adversary or adversaries are known to use, allowing network owners to visualize which TTPs could be a priority. Be aware, though, these attack heat map visualizations are not good tools for communicating impact to network owners or indicating the likelihood of different TTPs actually being used. Let's take a look at our scheduled task example to show how a gaps discussion might go. The issue we have come across is that the Windows 4698 events are not currently being collected, and the network owner has denied our initial request to enable the logging of these events. We schedule a meeting to discuss this particular gap in order to either convince them to begin collecting those logs or accept the risk that the gap presents. During the course of the discussion, we explain that scheduled tasks are a common method used by adversaries to maintain persistence on networks, and not having sufficient visibility of those events means we cannot verify if they are still in the network and where. We also explain that not having visibility of this means adversaries may be able to return to the network at any time, holding the whole network at risk. We point out that the additional logging won't require additional licenses or deploying new tools, as we are proposing using existing Windows auditing methods. Using open source resources, we show that several active APT groups are known to be using scheduled tasks to maintain persistence and move laterally. Supporting this discussion, we bring an attack navigator heat map showing the gaps we have identified, including the scheduled task gap. At the conclusion of the discussion, we have hopefully been able to persuade the network owner to modify the GPOs to collect the 4698 events. Recall that we are also looking for instances where an adversary scheduled a task on a remote host. An alternate method to using packet capture to find that activity is to use Sysmon's image load monitoring capability. This event logs when an executable loads a dynamic load library or DLL object during its execution. On Windows, when a process needs to make a connection over the network, one of the libraries it needs to load is mswsock.dll. Therefore, we can monitor for instances where a remote task may be scheduled by the common processes used to schedule tasks if we look for times where those executables, in this case scheduled tasks, MMC, and load that DLL. This method has several advantages over using packet capture, with the primary advantage being that it doesn't require any additional hardware to set up and use. And if Sysmon is already deployed in the environment and its logs are already being collected, there is no additional software to deploy. You will also likely have an easier time correlating the scheduled task to other malicious processes, as we will be able to follow the process chain back to all malicious processes. The downside is that it can potentially generate a lot of logs in the environment, depending how the scheduled task utilities are being used. If we want to pursue this method, it would be a good idea to test the configuration on a few hosts to gauge how much noise there is, and if it would even be worth pushing out to the larger environment. I have included an example Sysmon entry for capturing this activity if you want to try it yourself or play around with it. We could also use a rule like this for redundancy if we were worried about adversaries evading our network monitoring solution, or if we expect to have gaps in its deployment. Whether or not this redundancy is desirable or necessary is a decision that we need to make on a case-by-case basis, and it is something we will likely ask ourselves several times in this process. In our next section, we will discuss validating configuration of our sensor deployments. There are a couple of things we want to check up front before we start writing any analytics. For the purposes of this discussion, we'll be taking the perspective of checking the data collection from a seam, as that is ultimately where we want the data to be ending up, and it needs to be usable there. If there are issues in the data there, then there could be problems anywhere in the data flow chain. The first thing we want to ask ourselves is all the data we expect arriving from the sensors? This is more than just asking, do I see Windows security logs, and saying, great if I do. No. We need to also validate that the different types of data are coming in as well, along with all the content we need those events to contain. We also need to check to see if data from all the sources that we expect is arriving successfully. There are some common metrics we can use to do this, including counting how many hosts are sending each data type and comparing that to the number of hosts on the enterprise, listing the different devices sending data, and ensuring data is being collected for all of the relevant subnets by checking which IP addresses we have events from. Which metric you use will depend on what kind of event it is. Also, keep in mind that there will inevitably be some variability in the number of hosts and devices that report events at any given time, especially hosts. In offices today, users may take their laptops home where they are disconnected from the corporate network or just have the machines off. In either case, they will not report events, so we will have to expect we will likely never reach 100% of endpoints reporting at a given time. Once we ensure the data is in the seam, we need to check that it is being parsed correctly. Seams perform several important functions with data prior to the analyst using the data itself, including ingesting the data, parsing it into fields, and indexing it. They also may perform transformations on the data as it is ingested so that the analyst does not need to do it at search time. Often, the first thing we want to look at is the fields that have been made available for the analyst to use. We want to check that, at a minimum, all the fields contained in the raw or unparsed event are parsed out correctly, and that their associated data fields are also parsed correctly. Usually, seams handle these data extractions well, but some data types tend to cause issues for default settings. Data types that contain lots of special characters or spaces, like URLs, tend to cause problems for some parsers, so we should pay particular attention to those. Another common issue is Windows logs, as they tend to have repeated field names as a result of the way the log is structured. If we have any automated field transformations, like geolocation tags added to events or number conversions, we need to make sure those are being executed correctly as well. After we've ensured that all the kinds of data we want is in and usable, we can make sure that the data we are generating will meet our needs for creating the planned detections. In an ideal world, this step would not be necessary as we did significant research up to this point, but it is possible we made a mistake. Like we discussed earlier in this step, we can use adversary emulation techniques and tools to verify the required data is coming in. Again, we would execute particular techniques and then look for those events in the data. If we can find those events, then we know that at a minimum, any detection we write has a possibility of finding the event. Often it is easier when doing this to tightly focus searches looking for the given event in order to find it faster. Let's look at some of the questions we want to ask ourselves in the context of our scheduled task example. First, we need to check to see if any Windows security events are even reaching the seam. If they are, we can then check to see if we have any 4698 events in the analytics platform. If we don't find any, we may need to generate at least one to verify that the logs are coming in. It could be that there is no background events happening to find, thus requiring us to stimulate the environment. Second, we need to check the content of the events themselves. Are fields being parsed out, particularly those fields we know we will use like event ID, subject username, and user ID? Is the data associated with each of these fields correct? Once we've validated the events are coming in and parsed correctly, then we'll need to start looking at what kind of background noise there is, and if any of the events have characteristics of the malicious events we are trying to identify. For scheduled tasks, we could look at what subject username user ID pairs there are. Keep in mind we are not trying to write the detection yet, just assess what's already in the environment. We also want to schedule some remote tasks, with network owner permission, of course, to make sure we can see those kind of events as well. Let's review what we did in this step for the scheduled task example, and then do an exercise for credential dumping before wrapping up this section. Per the needs defined in step 3, we reconfigured the environment to begin collecting Windows security logs, as well as collecting 4698 events. We made sure that the logs got aggregated from all of the endpoints and ingested into the analysis platform. We developed a strategy that included collecting logs from all hosts as soon as possible and ingested continuously. Using group policy objects, we enabled auditing of other object events. We validated that the logs were reaching the seam and parsed correctly before executing a command that emulates one way an adversary can execute the malicious activity. Once the command was ran, we looked for it in the scene to make sure we could find it there. In this step, we evaluated the current state of sensors in the environment, assessed any gaps between the required data that we identified in step 3 and what we have now, and bridged or mitigated those gaps. Now that we have done that, we are postured well to develop our analytics for the next step. We will use the hypotheses and logic developed in step 2, combined with the data collected in this step to develop those analytics.